How to Live on Mars, a film by Gabe Patton. The planets, including Earth, are able to stay in their revolutional orbit by gravity from the Sun. The Sun's gravity affects the planets by using Newton's law of gravitation. Now, breaking this law down is quite simple. F is the gravitational force between two objects. M1 and M2 are the masses of the objects. G is the gravitational constant, a number that always stays the same, and R is the distance between the two objects. The R term is quadratic. R squared equals R times R, and it is in the denominator. This means that when the distance between two objects gets bigger, the gravitational force between them gets really small. In this case, Pluto would have the smallest gravitational pull on the Sun. We as humans act as planets around the Earth as the Earth and other planets do around the Sun. Earth's gravitational pull is 9.78 meters per second squared. As humans, we have adapted to Earth's gravitational pull. If humans were to move to Mars, they would have to adapt to Mars's gravitational pull. With Mars's gravitational pull being 3.711 meters squared, it is 62% less than Earth's gravitational pull. Being in Mars's low gravity for long periods of time would make our body systems freak out. Since they are used to Earth's gravity pulling them down and setting them into our body, Mars's would jumble them up and move them around in our body to places they're not supposed to be, which would make us sick. Gravity is not just a force, it's also a signal that tells the body how to act. For one thing, it tells muscles and bones how strong they must be. Muscle mass can vanish at a rate of 5% a week in zero or low gravity. Bones in space atrophy at a rate of about 1% a month. This can be catastrophic if you're in space for more than a few months at a time. Blood feels gravity too. On Earth, blood remains in pools at the bottom half of your body. When people stand, blood pressure can be high in their feet and legs. But in space, where the familiar pull of gravity is missing, the head-to-toe gradient vanishes. Blood pressure equalizes while you're up in space. That's why astronauts look odd. All their blood from their legs move up and throughout their body, so their upper half looks thicker and more puffy, while their bottom half, as in their legs and feet, are more thin. Colonists would have to make a gym or even a simple room where they would go every day and have machines that would work out their legs and arms and flush out their body systems in order to keep them fresh and strong. With our moon and our Earth, the Earth acts as the sun as the moon acts like the Earth. When I say this, I mean that the Earth acts as the sun, as in the Earth has a lot more mass than the moon does, causing the moon to orbit the Earth as the Earth orbits the sun. Mars's moons, Deimos and Phobos, are very small compared to Earth's moons. They are so small because Mars does not have enough gravity to have anything bigger than Deimos and Phobos to orbit itself. Because Deimos and Phobos is so small, they do not have enough density to make their shape round and circular, but instead they look more like a potato. Some scientists say that these moons are too small to be actual moons, but instead they're asteroids that Mars brought into its own gravitational orbit from the asteroid belt. While Phobos is noticeably bigger than Deimos, Phobos orbits Mars about 3 times a day, and every century it is moving 1.8 meters closer to the planet. Within 50 million years, it will either crash into Mars or break up and form a gorgeous ring around the planet. Scientists say that Deimos is too small to keep in orbit around Mars. Eventually, it's going to break off and be a lonely moon with no planet to orbit. Going back to the gravitational law by Newton, this is what keeps the planets the same distance away from the sun. Because planets' masses don't change very dramatically, Newton's law says that the gravitational force between planets and the sun will stay the same.